All right, so last, physicists looking for how the universe is put together as a whole. One set of rules that to rule them all and runs all of physics, explains everything we see. Again, about 1900, we thought we had it. Now we're in the land of a lot of things we can't explain real well. Quantum mechanics and relativity have nuked our understanding of how things work. Not that, but the idea that when we start breaking apart particles, we thought protons, electrons, neutrons combined were good. Then we started finding pions, muons, and all sorts of other garbage in the universe that look like these things, and yet don't appear very often on planet Earth, but we can collect them if we're careful with particle catchers, including things like we have mines in Utah where we collect things from the sun, try to catch neutrinos traveling through the Earth. These particles and this idea led to a explosion of what could explain the universe. Now, there is still an Einsteinian group out there. An Einsteinian group theoretically is still the central, this is how physics is done, this is the right way to do it, and we think this is our best explanation for the universe. Experimental data does support them. We talked about force particles before. That's grand unified theory. So grand unified theory says, look, all the forces are the same force, looked at from different lenses. So electricity is attraction between two particles. Gravity is the same thing. They're both bending the universe. They're both creating particles that travel through space. All of them are quantized. And ultimately, there's probably only a couple particles, 6 particles called quarks. And those 6 particles make up all the other particles we can find in the particle zoo that we've made. And the idea is a glued together idea from the old Einstein stuff. Okay? And it basically says, look, for every particle is an antiparticle. Has to be, because we started with nothing, and there was an initial explosion, all bang, bang, whatever. And that those particles are arranged in such a way that we don't have a lot of antiparticles in our neighborhood, which is good, because when they hit, they annihilate and create E equals mc squared. Those particles come in all sorts of things called quarks. Those quarks are 6 different flavors. Those 6 flavors make all the particles we see in the universe. Every force is the same force viewed at from a different lens. All of them are just F equals some constant, mm over r squared, or qq over r squared, or whatever the things are, based on how we're looking at the particular space we're in. And that's the grand unified theory in a nutshell. It is the theory I grew up with as a physicist. It's what we theoretically were going to believe. And the problem with it, is it's a 1920s idea, which was saved in the 1950s by a group of people finding something called a neutrino, saved in the 1970s by some people putting together the relativistic piece. But it's just every time there's a new finding in the universe, it doesn't explain it well enough. And we end up kind of gluing our pieces back together again to make up a new theory. Now, to be fair, in about 6 years ago, they discovered the 6th quark, which makes the set work. The problem with the 6th quark is it gave us 2 questions and only 1 answer. So again, it's not dead. We're still working on this theory. It's still a good theory. The universe could be made of 6 quarks. In fact, it may actually be made of 6 quarks. But it doesn't explain. We're starting to get in the land of where we have to use so many different rules to explain something. It doesn't feel like a grand unified theory. And physicists have always looked for, this is what the universe is. And so a second theory started to appear in the 1970s. The second theory is fascinating because it came from mathematicians, not physicists. Physicists wasn't even a physicist trying to work on physics. It was a mathematician who asked himself a very strange question. And his question was this. He said, if I make a string vibrate, there are certain harmonic frequencies you get. Get over here. Certain harmonic frequencies you get. And remember, harmonics was like something like this. So, oh man, I got to screw up myself so I can write on this thing. So I got a stick here, I got a string, I got another stick here. That when I flick this, there's certainly, I can get a this, I can get a one big one, I can get one that has like this roughly. I can get all these harmonic frequencies, and those are the harmonic frequencies. And he simply asked himself, What if the string went in 4 dimensions, and then what if it did it in 5 dimensions, and what if it went to 6 dimensions, what if it went 7 dimensions, and so on and so forth. So he was just kind of doing some math and having a good time. And he came up with this fun little thing where you could mathematically model how many different kinds of ways could it shake if you give itself 10 degrees of freedom or 11 degrees of freedom, whatever it is. Now, what happened here is as he was playing with the math, something really weird happened when he got to 11 dimensions. And what is it that's weird that happened? Well, he was trying to come up with something reasonable to figure out what's going on. So he figured the safest bet for speed, which is spring confined, should be the speed of light. So he threw in the speed of the wave would be equal to the speed of light. That's okay, that's fine. Nothing big there, he could pick any speed and it was fine. What he discovered was some very weird things happen. What he discovered was that when you flick the string, the harmonics come out in a certain way. The harmonics that come out a certain way would have energies which you could put a number to. Okay, fine. And he published his stuff and passed it around, and everybody thought that was great, wonderful. And then along came a set of quantum mechanicists. The quantum mechanicists saw this and thought, wait a second, I've seen this before. Where have I seen this before? So then they went in, and the quantum mechanicists said, look, let's make this box, this length. And again, I'm simplifying as best I can. Let's make this the Heisenberg uncertainty box. In other words, I can't go inside this box. So in other words, let's pretend that I have a loop or just a piece of string for which the two ends are so small I would not be able to figure out what's going on inside based on the physics I know how to do. And let's say I let it oscillate at 11 dimensions, what would I get? And the answer is you would get energy levels. The first energy level that corresponds exactly to the mass of an electron, as in E equals mc squared. That is how much energy you would have in this string if you let it vibrate in 11 dimensions and you set the boundaries to be the Heisenberg uncertainty box. A later harmonic is a proton's mass. Neutron's mass is another one, by the way. All the particle zoo things, muons, and so on, they all start to appear, come naturally out of this. Well, what did I do? I said, if you had a piece of string so small you couldn't see what it was doing, which would be if the universe had a string in it, that if you hit it with light, it would be too small to see what's going on inside. Well, why would it be impossible to see what's going on inside? Well, if it was a string, when you're looking for a particle, you're asking where the string is. The string's in the whole entire area. It's a nonsense question. The universe would spit out a nonsense answer. Yeah, I don't know. Now, you could monkey with the string, but the bottom line is you could never tell me exactly what's going on here because you think you're looking for a particle, you're actually finding a string. So this would explain why you can't look inside the box, because if the universe was made of strings, then what you're asking is, where is the particle? The particle is a vibration on this string, and it's the whole string, right? You can't find it inside the string because it's the string itself. What's the second thing we did to make this thing work? Well, the mathematician set this so this spring, the wave travels in this string at the speed of light. Well, didn't we just discuss that everything's traveling at the speed of light? If you're not traveling in one direction, you're traveling in the direction of time at the speed of light. So therefore, this wave would travel at the speed of light. So if I say the universe is made out of strings, I'll do. If I say the universe is made out of strings, and I say waves in these strings can only go at the speed of light, and the length of these strings is the Heisenberg uncertainty box, and I say it can vibrate in 11 dimensions, then I naturally, the reason why a electron has an electron mass, electrons where the mass is because when this thing vibrates, that's the first harmonic, is E equals mc squared. And the energy is equal to the mass of an electron. And this happens naturally from the math, which leads to a very strange situation. Is the universe not made out of tables, balls, rocks, and trees? Is it simply a series or a really long set of strings? If that's so, you as a human being are not mass and rocks and stone and carbon and water. You are instead a song, a series of oscillating strings. As you move around the room, these strings pick up the thing. By the way, it explains why it's quantum, right? Because I'm moving one string to another string. I can't stop in between the two, right? It's either this string or this string that is vibrating, but not both at the same time, and I can't move from one to the other. Basically, all that's happening is I'm vibrating this little. Now, again, they think they're mostly, the people at string theorists now talking about mostly think they're loops. And so when this string's got a vibration, once it deadens, this one picks it up. Quantum mechanics, right? Here or there, but not both. How fast does it travel? The wave can only travel the speed of light. Relativity, quantum mechanics, both explained. But now our universe just got very strange. What we think of as mass is really energy, and that, which makes sense because we know E equals mc squared. If I still a string, I would think, oh, I lost some mass. That creates energy, which would cause ripples in the other strings. This is called superstring theory. Superstring theory is the idea that the universe is made of strings because the math works really well. It explains everything we've seen, except for one very huge, epic problem. The bugaboo, if you're a string theorist, is the following. 11 dimensions? Show them to me. I tell you what, I'll give you left, right, up, down, forward, back. I'll give you that. But I'll give you time, right? Because we just talked about time. Time's a dimension. Okay, fine. You're now up to 4. How am I so weirdly out of place? Here we go. We have 4 dimensions. You have 4 dimensions. 7 more to go, man. 7 more. Find them for me. Now, you'll find physicists working really hard, and this is when you realize the theory has a long ways to go, because although this is elegant, it's beautiful, it explains physics so well in so many fundamental ways. Why are force particles different than other particles? Because they're oscillating in a different way. We can't see the mass propagating from one spot to another spot, but we know it's traveling. We can measure the traveling, right? So why is it different than the others? Well, because it's vibrating in the direction of force particle land. Okay. The problem, of course, is this. Although it explains everything nicely, gives us relativity, gives us quantum mechanics, makes it non-nonsense anymore. It's not that we don't know where the universe to keep track of particles. The universe knows the particle is a wave that's vibrating here. You're just asking the wrong question. You say, where's the particle? There's no particle there, dude. It's a wave. It's always been a wave, right? You can't keep track of a wave. It can't be in one place. There's always a range of where it's going to be because it's inside of the loop, vibrating that loop. It explains all these really well, except the bugaboo. What's the bugaboo? You have 7 more dimensions, man. That's 8. Last day of school. 7 more dimensions. If you got 7 more dimensions, you need to show me. If you show me 2 dimensions I haven't seen before, I'll start blinding this. And there is the problem. The problem is string theory is elegant. It's beautiful. The math works wonderfully. Explains a lot of the universe. But it's a mathematical trick. Like I've never seen a string. I've never seen 11 dimensions. What are you talking about? Well, if the universe is explainable. See how beautiful that is? Yes, it's beautiful, but I've never seen a string, and I've never seen 11 dimensions. So physicists have a job to do, and that is what they're doing. There are physicists right now working very hard to figure out if they can find other dimensions. And so if you pick up books in the library, books at the bookstore, you'll find them talking about 11 dimensions. Why? Because string theory is cool. Bye, guys.